Okay, so hi everybody. Welcome to our District Interim 2 review, going over all of these answers. Hopefully you have tried this yourself first before you have come straight to the review to get all the answers. Remember, the test isn't going to look like this. It's just going to have all of this stuff on it. So let's talk about the terminology. That terminology that you see right there is a really good summary of the most of the things that you are going to need to be able to know, understand, and apply on this test. And while I personally don't think this test is hard, I do think because of all of this terminology, that many of you will find this test to be difficult just because you're just not sure what all this is asking you and talking to you about. So that is why your personal word walls become so very important to you. And that's why I also made you have to do the ionic bonding personal word wall to go with this, because we have a lot of new terminology even in ionic bonding. Okay, so let's go ahead and get started with measurement as our first thing. And one of the first things that you have to be able to do is you have to be able to look at your at your graduated cylinder and read the scale and be able to say what the measurement is. And so if you notice, between 60 and 70 on the scale, there are 10 lines. That means each line is worth 1 milliliter. And that means that you could estimate to the first decimal place or halfway between a 1 milliliter line. So that means that since the measurement bottom of the meniscus is coming in right at the 67 line, we would call this 67.0 milliliters. Okay, so we would definitely want to call it that, and we would show it to the correct decimal place as well. Remembering that you can measure halfway in between the lines pretty accurately, and that's what that device is showing you. Explaining the use of the displacement method. So the displacement method is used to measure the volume of an irregular object by subtracting so you're going to subtract the initial volume, which is the volume in this graduated cylinder, from the final volume, which is the volume in this graduated cylinder, and the difference between the two ends up being the volume of your irregular object. Okay, and then the last part is we want to be able to talk about the level of accuracy that can be expected from this equipment. So as we've already said, this equipment can be measured to the tenths place or the 0.1 milliliter value. Okay, and so something that would be more accurate would be something that could be measured to the 0.01 milliliter value, but that's what this is referring to here. Okay, on we go. Now, the next part is we're going to arrange the words in the word bank to go in their appropriate places in the diagram below. And we are comparing physical changes to chemical changes and things that occur in both. So I'm actually going to go grab these things and pull them over into where they go. So melting is a physical change, but burning is a chemical change. And decomposition is a chemical change. But freezing, that's just a physical change. And dissolving is just a physical change, as is evaporation. But oxidation is actually a chemical change. Now, this term reversible, you have been taught that chemical changes are not reversible. It turns out that, and we're going to go with that, chemical changes are not reversible. So physical changes in our understanding right now are that those are the only things that can be reversible. But truthfully, there are chemical changes that can be reversed. But for our purposes right now, we're going to go with physical changes are the only things that can be reversed. Chemical changes, a new substance forms. Condensation is a physical change. Rusting, chemical change. Explosion, chemical change. A change of state, in other words, a change from a solid to a liquid to a gas. That is just going to be a physical change. If a gas is formed like from the result of a chemical reaction, a gas is formed, a new substance is formed, that's going to be a chemical change. This idea of mass is conserved, meaning that mass is not gained or lost, it is just changed, and that's going to happen in both places. Chemical change, you are going to have energy being evolved. In chemical changes, bonds will be broken and new bonds will be formed. All right, so that kind of gives you a good overall. They both involve some kind of change. And I'm going to go ahead and say, might we see a change of state in a chemical change as well? Yeah, we might see a change of state in a chemical change as well, especially when that new substance forms. So there are, that is kind of your overall of the physical change versus chemical change. So then we go on to identifying the following as either an element, a compound, a homogeneous mixture, or a heterogeneous mixture. And so salt and pepper, we are going to call that heterogeneous mixture. Copper and zinc fuse together by melting. Melting is just a physical change, and that means that we are talking about two different metals. Copper is an orange metal and zinc is a silver metal. So if they're fused together, they're not mixed, so you can't see them apart. They're just melted together. So we would call that a heterogeneous mixture. Salt water can be separated by boiling, but if you think about what a salt water solution looks like, you can agree that it looks all the same. So that's going to be a homogeneous mixture. Sodium chloride, which can only be separated by a chemical change, that is going to be a compound. Sodium is just a plain old element. So is chlorine. Carbon dioxide gas rising out of a soda. So what we're looking at here is the soda overall, and you can see that, let's say it's Sprite. So we have Sprite, and we open the Sprite bottle, and we can see bubbles forming and floating to the top. So this ends up being a heterogeneous mixture because I can see the bubbles floating to the top, and I can see the clear liquid. And then finally, a wax candle burning to form carbon dioxide and water vapor. So what is this? Is this a heterogeneous mixture or a pure substance? Well, the candle is not naturally just going to evaporate into carbon dioxide and water, so it is going to have to undergo a chemical change, and things that have to undergo a chemical change have to be a compound. Okay, please remember that your elements are never going to undergo, let's write that down, elements will not be changed to new elements through any type of change. So please make sure you understand that elements do not undergo a change. Can elements be combined to form compounds? Yes, but they will not be changed to new elements through any type of change. Okay, so we're going to go on to classifying the properties below as physical or chemical, and then choose if it is an intensive or extensive property. So mass is a physical property, and it is extensive because it can be changed by amount. Odor is a chemical property. I can see how we might argue that, but it is always so. For instance, odor, a rotten egg smell is an odor. That would be a chemical smell coming off of it, and no matter how much of it you have, it's still going to give off that odor. So that is an intensive property. Length, again, is going to be a physical property, and it's going to rely on amount, so that's extensive. Hardness and ductility is going to be physical, and it's not going to rely on how much of something you have, so that's going to be intensive. So metals will have that as an intensive property. How it reacts with an acid is going to be a chemical property, and it will not depend upon amount. So that will be an intensive property. Color and luster is a physical property, and it's going to be not depend on amount, so it will be intensive. Density will be a physical property, and it will be intensive. So the density does not change with amount, as will be melting point and intensive. For melting point physical and intensive, weight is not going to be chemical. It is simply going to be physical, but it will depend upon amount. So that is extensive. And then its flammability, tendency to corrode, or its ability to be lit on fire. Those are all chemical types of changes, and they do not depend upon amount, so they are intensive. Okay, our next type of calculation that we have to do is dependent upon density equation. So density is equal to mass over volume. And so our problem says, first it says there's a picture here that says how tightly packed the matter is going to give us the amount of mass in a given space. So gases are least dense, liquids a little bit more, and solids are the most dense of all. So our problem says calculate the density of a toxic gas that makes up 25 centimeters cubed of space and has a mass of 20.0 grams. Compare this gas to air's density, which is 1.225 grams per centimeter cubed. And then answer the question, if both of these gases were pumped into your room, should you run out standing up as tall as you can, or should you crawl out? Explain. Okay, so first, let's calculate the density of the toxic gas. And we are going to do mass divided by volume. So that is going to be 20 grams divided by 25 centimeters cubed. And so we will get that calculation, and I'm going to quickly grab my calculator. And my calculation will be 0.80, and that is going to be grams per centimeter cubed. All right, so the answer to the question is, there is our density. So less dense things float over more dense. So you should crawl out of the room to avoid the toxic gas at the top of the room. How about that? Did you guys get it right? I hope so. Define the term isotope. Isotopes are elements with the same number of protons, but a different number of electrons, causing a different mass number. And I said electrons. Electrons is incorrect. Instead, we should say neutrons. And I spelled neutrons wrong, everybody. There we go. So causing a different mass number, different number of neutrons. Okay. So on this next part, we are going to need to be able to, and I'm gonna move this down here because it appears I need this to be able to be seen here. So I'm gonna move it back up here. There we go, so I can see it. So there are some isotopes in the box there. So what I want to be able to do is I want to determine the protons, neutrons, and electrons for each of the isotopes. So the first thing I have is neon. And neon, the number of protons is always written at the bottom in isotopic notation. So that means I can say neon has 10 protons. The other way I can figure this out is I can go look at a periodic table and find out what its atomic number are. Then, since neon does not have a charge, I can also say that its electrons are 10, but I'm going to have to subtract the 21 minus the 10 to give me the number of neutrons, which will be 11. And I'm going to repeat that process for each of the other elements. Carbon, looking that one up on the periodic table because I don't have the same notation, tells me that I have 6 protons. and my neutrons are going to be 14 minus 6 equals 8, and my electrons, because there's no charge, are going to be the same as my protons. All right, the next one is oxygen, and I can see that oxygen has 8 protons based on the isotopic notation, and then I'm going to do 16 minus 8 equals 8 for neutrons, and then my electrons, I have to be careful here because my charge is -2. And if my charge is -2 and I know my protons are 8, then I want to know what my electrons are. So 8 minus 10 is going to be what gives me the -2 there. Okay, my last one is sodium. Sodium is number 11 on the periodic table. I can find its number of neutrons by doing 23 minus 11 to give me 12 neutrons. And my number of electrons is going to be the charge equal to protons minus the number of electrons. So therefore, my number of electrons has to be, in this case, 10 as well. Hopefully you got all of those right. Okay, so the next part is we're going to calculate our average atomic mass of this unknown element, and then we're going to have to look at a periodic table to figure out what its identity is based on its mass. So I am going to pause this right here, and I'm going to let you pause right now and do your calculation, and then we'll come back and see how you did. Okay, so calculating the average atomic mass means that we have to be able to remember to do a few things. And the first thing is we're going to be able to take our isotopic masses times our percent abundance. But we have to be able to move the decimal place 2 places to the left on all of our percentages so that we end up, instead of 92.21, we end up with 0.9221 and 0.0470 and 0.0309. So always have to move our decimal place 2 places to the left. And then we have to add up each of the parts together, and we get 28.09. And so when we get this, that's our average atomic mass. And then we would have to go find, by looking at the masses on the periodic table, which mass is closer. Silicon resides between aluminum and phosphorus. Phosphorus has an atomic mass of higher than 30. Aluminum has an atomic mass of just higher than 26. And silicon is right there at that spot. So silicon was our correct answer here. So that's how we looked it up on the periodic table. You will need to also know the contributions of the following scientists to the modern atomic theory. So we have Thomson identified the negative particle in the atom using the cathode ray tube experiment. Rutherford identified the positive nucleus and the rest of the atom was mostly empty space. Chadwick, oh, by the way, he used the gold foil experiment. Chadwick identified the neutron and basically using deficiencies and I can't spell deficiencies, everybody. Deficiencies, still think it's wrong, in masses, to using deficiencies in the masses of atoms and isotopes. Okay, so he identified the neutron. Bohr is responsible for the planetary model of electrons in an atom. Okay, so those were our scientists. Our next thing we have to do is we have to be able to do some calculations. So I am going to fill in my calculations after I hit pause, and then we'll talk about all of the pieces and parts for you here. So that's where I'm going next. Okay, so what I'm doing right now is I am writing in the correct formula for magnesium hydroxide after I crisscross the charges. And the next thing I'm going to do is calculate the molar mass. And to do that, add up all of the parts. So magnesium has a mass of 24.31. Let me make sure I type that in the right place. So molar mass, 24.31. And I'm going to add that to 2 times 16. And for 2 oxygens, because remember the 2 distributes inside. And then I'm going to add that to 2 times 1 for the hydrogen, giving me a total of 32 plus 24 plus 2. So 32 plus 36 is 58.31. I think I just did that right. Checking it on my calculator first, because you know what my math skills are like. In my head sometimes it is 58.31. That is my molar mass. And then I'm going to need to be able to calculate the number of moles. So moles first. So moles is going to be equal to grams divided by molar mass. And so doing that, I am going to have, the problem gave me 15.0 grams divided by now 58.31. So my moles is going to be 0.257 moles. And then I'm going to calculate then the number of particles. And the particles are the same as saying if I have formula, mass, formula units, or molecules. And so that's going to be particles are equal to moles times Avogadro's number. All right, so that means that I have 0.257 moles, and I'm going to multiply that by Avogadro's number, 6.02 times 10 raised to the 23rd. And so then my answer for this one is going to come out to 0.257 times 6.02, and I'm going to get 1.55 times 10 raised to the 23rd power. And the unit label on this, not what I wanted, hang on. The unit label on this is going to be particles of MgOH2. All right, so go ahead and pause this video next to see how to do the next one. And the next one is going to be for lead. And so lead, as you might know, is Pb, just plain old Pb. And you know already that the molar mass for an atom is just its molar mass from the periodic table. So that is 207.8 if I'm not mistaken. So I'm going to actually go look at my Pb 207.2. I was wrong. 207.2 is my molar mass, and that's unit label is grams per mole. And then I'm going to calculate moles by doing grams, 15.0 divided by 207.2. So my number of moles comes out to 0.0724 moles. And then I'm going to calculate particles by taking my 0.0724 moles and multiplying it by Avogadro's number. And that should give me my number of moles. Okay, once I calculated that, I got 4.36 times 10 to the 22 particles of lead. So we're going to go through and we're going to do that next on the copper 2 chlorate. Going to repeat all those processes again. First thing I have to do is I have to write copper 2 chlorate correctly by crisscrossing my charges. So I end up with Cu parentheses ClO3 close parentheses 2. because the copper is copper 2, which means copper 2 plus, and the chlorate is ClO3 minus. So I had to crisscross my charges to get CuClO3 2. All right, so my molar mass is going to be equal to all of these masses added up. And I'm going to go ahead and go look up all those molar masses and show you what that. Okay, so after I wrote my formula of copper 2 chlorate, then I added up the molar masses for the copper, 63.55, and 2 times the molar mass for chlorine, because of the 2 on the outside of the parentheses, and 6 times the molar mass for oxygen, because the 2 multiplies by the 3 next to the oxygen. So I ended up with 230.45 grams per mole. So the next thing I'm going to do is I'm going to calculate moles by taking my number of grams and dividing it by my number of the molar mass, 230.45. And I'm going to do that both for sodium and for copper 2 chlorate. Okay, so I calculated the moles when I divided 15.0 divided by the molar mass. I got 0.0651 moles. And then to find particles, I am multiplying the number of moles by Avogadro's number, and that is giving me 3.92 times 10 raised to the 22nd power, and that's going to give us the number of particles of the copper 2 chlorate. I can repeat the same process for the sodium. When I found the number of moles is 0.652, and I'm going to multiply it by Avogadro's number, and for this one I'm going to end up with 3.93 times 10 raised to the 23rd power. Oh, not what I wanted to do, everybody. Here we go. Raised to the 23rd power, and that's going to give me the particles of the sodium. So you do have to be able to do your calculations no matter what it asks for you to do. All right, so the next thing we have is, and I'm wondering where my periodic table went. Let's see if we can, I'm just wondering, my periodic table has disappeared here, but we need to be able to name all the group names. And I'm just looking for my periodic table. It has gone. So we are going to insert a periodic table here. I'm going to go find that periodic table again. I don't know where my periodic table went, but we're going to find it. And I need pictures. There we go. And periodic table. There it is. Okay. So I put my periodic table in, and the first thing I want to do is I want to be able to identify all the group names. And so group number 1 you need to remember are the alkali or alkaline metals. And then the next one is alkali earth metals. And then the group in between 2 and 3 at period 6 and 7, those are the inner transition metals. And the groups 3 through 12 are just the plain old transition metals. And then group 13 is called normally the aluminum group. Group 14 is called the carbon group. Group 15 is called the nitrogen group. Normally in more recent times, the next group is called the oxygen group, but you might see it also get called the chalcogen group. Group 17 is called the halogens, and group 18, of course, is called the noble gases. Okay, so then we want to go identify the trends of atomic radius, ionization energy, and electron negativity using directional arrows. So what I'm going to do is I'm going to try here to, I'm going to draw them in. If it is possible for you to show them, you might draw arrows in above or below the periodic table, but I'm going to draw them in on my periodic table. So in this case, my periodic table has increasing this way, ionization energy and electron negativity. And it is also increasing from the bottom to the top as well. Okay, so that was ionization energy and electron negativity. The atomic radius is actually going to be increasing this way. This is going to be atomic. Oh boy, that's fat. Change that back to this. That's going to be atomic radius. AT rad. Okay. And that atomic radius is also going to increase this way as well. I need to go make that bigger. So it's also going to increase this way as well. If you want to remember, if you're going, well, I'm never going to remember that, Mrs. Shiro, then it is certainly okay for you to draw in our two memory things that we use. So for instance, atomic radius shows you the change in size by drawing in the snowman. So let me make sure that gets bigger, so the snowman is atomic radius getting bigger this way, but getting smaller this way. That's our snowman, and that's going to be AR. Now, our snow cone, which is large at the top but small at the bottom, is going to represent our ionization energy and our electron negativity. So IE and electron negativity. And so you do need to remember what these trends look like as you go across and down the periodic table, because as you're going to see on the very next question, you are going to be asked what to put these in order. So now that we've got that, let's go ahead and scroll down to the next question. And the next question is asking us to place the following elements in order of greatest to least atomic radius. Okay, so let's go find these greatest to least atomic radius, and this is going to be zinc, strontium, chlorine, krypton, and magnesium. So let's go back up here and let's go label, find those. We have zinc, strontium, chlorine, krypton, and magnesium. I think I got them all. I hope I did. So if I were putting these in order, I would have to say that greatest to least is what it asked for. So strontium first, it has the most energy levels, followed by zinc, then getting smaller to krypton, followed by magnesium, and then getting smaller to chlorine of all. So if I were putting these in order, it would be strontium, zinc, krypton, magnesium, chlorine. All right. So then what about our next example? Let's go ahead and draw that or write that into our answer here. So we would have this in order of strontium, zinc, krypton, magnesium, chlorine, greatest to least. So then we want to do increasing ionization energy. Remember, that trend is in the opposite direction. So let's go see if we can find those on our periodic table. So let's go ahead and go up to, and those are which ones again? Tin, lead, bromine, potassium, sulfur. Tin, lead, bromine, potassium, sulfur. So I've got tin, oops. I've got tin, lead, bromine, potassium, there's potassium, and sulfur. We are going from least to greatest. So that means lead is going to be first, least, tin is next, potassium is next, increasing to bromine, and then sulfur. Remember, increasing up and increasing from the left to the right. Okay, so let's go write that all down on our answers here. So we would start with, we would have lead first, then tin, then bromine, then potassium, then sulfur. All right. So then we also need to pay attention to our sublevels on the periodic table. So let's scroll back up to our periodic table and make sure that everybody knows where our sublevels are and where they fit in terms of everything. So groups 1 and 2 are in S sublevel. Groups 3 through 12 are in the D sublevel. Groups 13 through 18 are in the P sublevel, and then the F sublevel. So let's make sure that we can use the periodic table to identify some elements. And so our elements are going to be, which elements do we want to? Argon, iron, and chlorine. So we're going to do that work right up here. So the first one that we are going to identify is argon. And that means that we are going to start from the top. In other words, 1s2 followed by 2s2. Here's 2s2 and 2p6. Dropping down, we're at 3s2, and we're going to end with 3p6. So let's go do that one first. And that's what I want. So let's go do that one first. Yes, I know those things are still on there. Don't worry. So we would have 1s2, 2s2, 2p6, 3s2, 3p6, 4s. Oh, stopping. We stopped at 3p6 because that's where argon goes. If we were going on to, if we were stopping at chlorine instead of argon, then we would have had all the same things. 1s2, 2s2, 2p6, 3s2, 3p. But because chlorine is one less electron than argon, then we would have ended at 3p5. Now, what about iron? Iron has all those same things as argon. 1s2, 2s2, 2p6, 3s2, 3p6. That's argon, but we have to go on to iron, which then leads us to 4s2 and 3d, and it counts over to 3d6. And so that those are going to be the electron configurations that you need to be able to use and identify elements from. Okay, so now we are on the metals and non-metals part of things. And this is getting to be a really long video. So I'm going to stop right here. Okay, so by now you ought to be able to have the idea of what are the properties of metals and non-metals, and that is going to be asked of you on this test, as well as what is the octet rule. And that is also something that will be referred to on this test. So I've filled both of those things in. Being able to describe the transfer of electrons in potassium sulfate in terms of sulfide, in terms of quantity and whether they are gained or lost. Metals lose their valence electrons to nonmetals, which gain them to complete their octet. So potassium loses 1 electron to sulfide, which gains 2 electrons, 1 from each potassium. So then we have, there's the picture. I went ahead and used a Google picture for you to be able to see what was going on there. And that's kind of how ionic bonding occurs, drawing the dot diagrams out and being able to show the movement of electrons. That is going to be something that comes up on your test. So it will be something that you want to make sure that you are aware of and have paid attention to. We did start this whole unit with that particular sort of picturing. Okay, so for this final part, we're just going to go kind of running through all of the different things that we can name or write the formulas of. So I have CaCl2, which is calcium chloride. Noticing that I did not name it with Roman numerals because it is not a transition metal, and I did not name it with an ATE or ITE, and that's because it is not a polyatomic. Sodium bromide has a Na1 plus and a Br1 minus, so we simply get to write this as NaBr for its formula. Magnesium fluoride is the combination of Mg2 plus and F1 minus, so this becomes MgF2, magnesium fluoride. And then we get to name Al2O3, and this is aluminum oxide. Notice I am not naming it with Roman numerals because it is not a transition metal, so aluminum oxide. Then we need to be able to make sure that we correctly write the formula of copper 2 sulfide. You know that copper is a 2+ ion because of those Roman numerals, and you look up sulfur on the periodic table, you find it is S2-. So it ends up with CuS because the 2+ and 2- cancel each other out. This next example, however, is one of the special ones that fall into group number 16 that behaves a lot like transition metals, so we use it with Roman numerals. So this is going to be lead, Roman numeral 3, and you might be going, oh, how'd they get that? So this is going to be lead Roman numeral 3 oxide, and that's because I'm going to uncrisscross the 3 and the 2, and that's going to tell me that it should be lead with a 3+ charge. Okay, my next one is going to be aluminum phosphide, and notice I am not using anything but IDE endings because all of these were just single metal or single nonmetals, not polyatomics. Now we're going to get into some polyatomics, and so we need to make sure that we name these correctly. Magnesium is not a transition metal, so I'm not going to name it with a Roman numeral. Instead, I'm just going to call it magnesium, and then I'm going to name the name of that polyatomic, which is chromate. Okay, so that's going to be called magnesium chromate. Next one, I have barium hydroxide, which is a combination of Ba2+ and OH with a 1- charge. So I end up with BaOH, whoops, put the 2 in the wrong place, BaOH2, just like that, with the 2 on the outside of the parentheses. The next one is a metal with a nonmetal polyatomic. So this is going to be potassium, and chlorate is the polyatomic name. And yes, I would look these up on my polyatomic list. The next one is iron 3 oxide, and iron is one of our Roman numerals being used because it is one of our transition metals. And my last one that we are going to do is going to be barium, which is not a transition metal, so no Roman numeral, and then that is a polyatomic, so this is a carbonate by looking it up on the periodic table. All right, and I believe, in fact, we have come to the end of our review. Fill in metal.